Looking at this situation, I have a stick shift car, and also until last month, my garage door was manual. So in order to pull into the garage, I pull up the driveway, which is a hill here, and then I park the car at the top of the driveway. And then I get out over here and open up the garage, and then I get back in the car and drive into the garage. So the problem that happens is that the driveway's on a hill, and so if you don't put the park brake on when you get out of the car, then the car will roll down the hill. So we'll show, all right, so the car would stop about here, and then here is the front view of the car. And so then we would park here, you would come around, open the garage door, come back to the car, get in, and then be able to drive it. So a few days after I got my car, I pulled up to the top of the driveway, got out, went, opened the garage door, walked back out, and my car was gone. And I thought, oh gosh. And so I looked down the driveway, and there was my car way down at the end of the driveway here. And it was rolling across, it was going to hit my neighbor's house across the street. And so I started running after the car, opened the door while it was moving, opened the driver's side door, hopped in, slammed on the brakes, and it came to a stop like 2 feet from my neighbor's mailbox. So it was a little bit of an adrenaline situation, but everything worked out okay. And now I always remember, put on the emergency brake before you get out of the car. So we're going to do some calculations here that involve this situation and how fast the car is moving and how much braking force you need and how long it's going to take to stop and all that kind of thing. We draw this out. The driveway is on a slope, so we'll have that. And we'll say that then you come to the end of the driveway and then the street is pretty flat. So we'll say state 1, top of driveway. State 2, bottom of driveway. State 3 is when I actually jumped into the car and slammed on the brakes. And then state 4 is where the car stopped. And there is friction on all of this. Now, the friction, when the car is just rolling, the friction doesn't really matter. It just prevents the car from slipping. Once I slammed on the brakes and the wheels locked up, then the friction is what's going to help stop the car. So we'll put coefficient of friction there, mu. And we need to know the length here of the driveway. We need to know the angle of the driveway, and we'll call this angle gamma because the wheels are going to be rolling and we don't want to get theta out of the wheels mixed up with the theta of the driveway. And then we have the car. So draw the car. Few parameters about the vehicle. So we need to know mass of the vehicle. Really, we need to know mass of the body of the vehicle and then the mass and the radius of each wheel. So we'll say MB for the mass of the body and then MW and R for wheel size. So if we're given here, car rolls downhill and we'll be given mass of the body of the car. And so a Mazda, this is a Mazda, which is kind of a lighter car, and it weighs about 1,400 kilograms or 3,100 pounds. So but that's split up between the body and the wheels. So I'm going to say each wheel, MW, weighs 25 kilograms. which is about 55 pounds. And then there are 4 of those, so that'll be 100 kilograms. And then we need the 1,300 kilograms for the body. So combined, the body plus the 4 wheels is going to be 1,400. So we'll just say M total equals 1,400 kilograms. And then length of the driveway and angle of the driveway. So length of the driveway is about 20 meters. And the angle of the driveway, gamma, is about 15 degrees. And then coefficient of friction between the tires and the dry ground, we will say that is 0.7. So it's anywhere from like 0.7 to 0.8. But since I got the car used, I'm going to say the tires were worn down. So we'll have to go with 0.7. So we've got all these parameters. Let's think, do we need anything else? I think we can do that here. So we need to find a lot of different things. We'll say 1, inertia of the wheel. 2, we need to find energy of the car. 3, we need to find speed at the bottom of the hill. We'll call that speed at point 2. And 4, we need to find stopping distance. So we'll say that between 3 and 4 here, that distance is D. We need to find the stopping distance D. And we'll also do a hypothetical here. Well, we'll also say time to stop. So 5, time to stop. And then we'll do a hypothetical. What if I hadn't made it into the car in time and the car smashed into my neighbor's mailbox? Say that the mailbox state 5 would have been the mailbox. So we'll say if the car had just rolled into the mailbox, then what would be the post-collision speed of the car mailbox combination, assuming a plastic collision? And we'll be given that the mass of the mailbox is 15 kilograms. So mailbox is about 33 pounds. Okay, so starting off with the very beginning, inertia of the wheels. So we'll say 1 IW wheel inertia. So IW, we will approximate the wheel as a disc. And that is going to be 1/2 mass of wheel times radius of wheel squared. So we'll have 4 wheels. So this IW is just for one single wheel. So if we put in 1/2 times the mass of wheel, which is 25 kilograms, times the radius of the wheel, which is, did we put that? We need the size of the wheel. Okay, so radius of the wheel. My wheels are about 24 inches diameter. So that would be about a 12-inch radius, which is about 30 centimeters. Okay, so the 30 centimeters is 0.3 meters. Square that. So put that into a calculator. What do you get for inertia of the wheel? 1.125 kilograms per meter cubed for one wheel. So step 2 is find the energy of the car. Well, we're going to assume that energy is conserved from the top to the bottom of the hill, because even though friction is on the hill, the friction is not preventing it's not preventing the car from, or like it's not draining energy from the car. It's just allowing the wheels to roll, and it's not, the car is not skidding at that point. So energy is conserved from the top of the hill to the bottom of the hill. So we'll say step 2, we need energy of the car. So if energy is conserved from the top of the hill to the bottom of the hill, then that means that energy at state 1 equals energy at state 2. And so that means that the potential energy of the car at state 1, when it was at the top of the driveway before it started sliding, is going to equal the kinetic energy of the vehicle at state 2 when it's at the bottom of the hill. So it starts at speed 0 at the top of the hill because it was just sitting there when I got out of it. And then it reached the bottom of the hill, and that's going to be its max speed. Because once it starts going across the flat ground, it's not going to increase its speed anymore. So we will say here, okay, energy at 1, energy at 2. So we need to know whether we calculate potential energy or kinetic energy. And right now we don't know the speed, so we got to calculate potential energy. So we'll say that potential energy at 1 equals mass of the car times gravity times height of the hill. Now we don't know the height of the driveway, but we could figure it out because here we have a triangle. So we have H over here, and then we have L, and we have gamma. So H is just L sine gamma. Okay. So the M here is total mass of the car. So the body plus the 4 wheels, which is that 1,400 kilograms total. So 1,400 times 9.81 times L, which is the 20 meters, sine of gamma, which is 15 degrees. So what do you get for total energy? So total energy here is 71,092 joules. And we'll just say that is energy of the car. And this is the energy that the car would have at states 1 at the top of the hill, 2 at the bottom of the hill, and 3 when I jumped into it. So energy is conserved across all of those states. Now, we do have a drag force acting on the car. So technically energy is not conserved, but the magnitude of the drag force compared to the mass of the vehicle is probably insignificant. But we can go ahead actually and calculate drag force. Let's say CD. So CD for my car, it's a sport. So I'm going to say it's got a low drag coefficient, and we're going to go with 0.2. And we know that density of air equals 1.225 kilograms per meter cubed. And I do not know if it was windy on that day or not because I was not thinking about that. So we're just going to go with no wind. Okay, so we'll call this 0 and just find rho air. Or sorry, find drag force. So drag force equals 1/2 rho CD V squared A. So we're going to calculate this drag force, and then we're going to compare the drag force to the force of the vehicle that's going down the plane. And if the drag force is more than 10% of that, then we have to account for it. If it's less than 10%, then we can say it's insignificant. So the point of what we're doing here is we're going to calculate drag force and see if it's small enough that we can ignore it. So we'll calculate the force here. Now the area of the vehicle, we need to know. I'll draw the back of the car here. We're going to approximate this here as a rectangle. It's actually a lot less curved than I drew it. So rectangle is a pretty good approximation. And W and H. So we're going to say that H, it is maybe 0.9 meters high, and W is maybe 1.5 meters wide. So here we have 1/2 times 1.225 times the CD, which is 0.2 times V. We don't know V, but we were supposed to figure it out. So I'll just say V squared. We'll come back to that one. Times A, which is W times H, which is 0.9 times the 1.5. Okay, so we'll have to find drag force, but to find drag force, we need to know speed. So we're going to say that at the top of the hill, drag force is 0 because the car wasn't moving. At the bottom, there will be a drag force, but we need to know how fast the car is moving in order to find it. So we'll go ahead and say part 3 here, which was finding speed at the bottom of the hill. We can use conservation of energy. So from state 1 to state 2, energy is conserved. So we have kinetic energy at state 2, the bottom of the hill, equals potential energy at state 1, just like we found for energy of the car over there. So we have the potential energy at state 1, which is mg L sine gamma, equals the kinetic energy at state 2. So the kinetic energy here is going to include a linear component and an angular component because we have translation and rotation going on. So the translation component, the 1/2 mv squared, is going to include the total mass of the vehicle because the body is translating and the wheels are translating. The whole thing is moving down. If the wheels were only rotating, then they would be not connected to the body, and that's not true. So I'll just put T here for total mass. So we have a 1/2 mv squared plus the rotational energy, which is for 4 wheels. So we have a 4 times 1/2 inertia of the wheel and omega squared. So omega of the wheel, we remember from physics, omega equals V over R. So we can erase this, and this is going to be a V squared over an R squared. Okay, so we related the angular velocity and the linear velocity of the wheel because there was a point touching the ground, and therefore they had to be related. So we put numbers in here. This mgl sine theta, we figured out before here, energy of the car was the 71,000. So we'll have 71092 equals 1/2. Okay, well, we have a V squared buried in both of these. So let's extract that V squared. V squared times 1/2 mt, total mass, plus this 4 times 1/2 is just 2 IW over R squared. So we just pulled that V squared out. So 71092 equals V squared times 1/2 times total mass, which is 1400, plus 2 times that IW, which we calculated as 1.225, divide by the R squared, which is 0.3, square that. So plug that into a calculator, take square root, and what do you get for V? So if we do this multiplication, we get 9.9 meters per second equals V. So now we can go ahead and take this 9.9 and plug that in over here where we had the V squared. So I'm going to erase that, and then I'll just write this in a different color so we see that we put it in. 9.9, boy, that's hard to see. 16.2 newtons equals the drag force. So we need to compare to see if we even have to bother with including this drag force in our future calculations as far as like, will the speed at 3 be the same as the speed at 2? Or is the wind going to slow the car down enough we need to compare the drag force to the weight of the car that was pushing down the hill. So the drag force at this point is going to be like some fraction of how much of that car was how much force was actually making the car accelerate. Was the drag force slowing it down very much or not? So we're going to look at that component that's pushing down the hill. So if we say, here is the free body diagram of the car. So we have weight of the car, mg, we have normal force, and then we've got the drag force pushing back. And then we have our coordinate frame x in the direction of motion and y perpendicular. All right, so the component of the weight, here's gamma, the component of the weight that's pushing in the x direction is the mg sine gamma that is pushing down the plane. So we're going to see, is drag force enough that it significantly slows down the car? Let's just find out how much is mg sine gamma, and then we'll compare that to the drag force. So this is similar to doing a static check, which we do the static check if we have a block on a plane. In this case, the car is rolling, so it's not friction is going to prevent it, but we do have the drag force acting on it. So we'll kind of compare that. So if we do the m times g times sine of gamma, then we'll have 1400 times 9.81 times sine 15. And for that, we get 3555 newtons. Okay. So this 3555 newtons is the weight that points down the plane. And the 16.2 is a drag force. So the drag force basically is way insignificant compared to the vehicle. So we're going to be able to ignore that drag force in the rest of our calculations here, as far as it's not really going to slow the car down very much from state 2 to state 3 or state 4. So that's like a 0.5%. So really easy to ignore. 0.5% at this point. If it's less than 1%, I'd say you can pretty much always ignore it. 4, which is that stopping distance. So how long did it take, once I got in the car, how long did it take me to stop it? Once I was in the car and I slammed on the brakes, the wheels locked up. So the car is basically skidding from 3 to 4. So at that point, we can just treat it the same as we did sort of for the roller coaster problems previously. So for part 4, which is stopping distance d, then we know that the energy at state 3 plus the work from 3 to 4 equals energy at state 4. Now, energy at state 4 is 0 because the car has stopped and it's on the ground. So we will just have that initial energy, which we had calculated here for energy of the car. So we'll say energy of the car, and then minus the work by friction. So we have minus the friction force times the stopping distance equals 0. So that's going to be energy of the car over friction force equals the stopping distance. Okay, now the friction force acting on the car is going to be the friction force when the car is flat now. So we basically have, we draw our free body diagram, then we will have the mg, we will have the normal force, we will have the friction force, and we can ignore the drag. So the friction force here is, let's see, the coefficient times the normal force. So we have energy of the car over friction, which is coefficient times normal force, mg, mu mg. Okay, so here's another situation where we might want to see, all right, well, how does drag force compare to friction? Considering that the coefficient of friction is 0.7, which is way bigger than the sine of 15 degrees, where the coefficient of friction or sine of 15 degrees is probably like 0.3 or something low, then the friction force is going to be even bigger than the amount of weight that was pulling down the plane. So again, drag force here is negligible compared to that. So we will put these in and say that we have 71,092 over the mu mg, which is 0.7 times the 1400 times the 9.81. And what do you get for stopping distance? All right, so this comes out to 7.4 meters equals the stopping distance. And just for fun, we'll compare, what if we had considered drag force? What would our new stopping distance be? For that, we'll just need we'll do a different calculation down here. So D, I'll call it D sub D if we're considering drag. 71092 over 0.7 times 1400 times 9.81 minus, or really we're adding to that the 16 that calls from the drag force, so 16.2. So if you put that into your calculator now, what does the new D come out to be? Okay, so it comes out to be 7.38 instead of 7.39. So it's still 7.4 equals D. So you can see that the drag force was insignificant because the car was going so slowly. Now, if I had been driving on the interstate, or I don't know, say the car was going like 60 miles per hour and instead of like 9.9 meters per second, then maybe we would have to consider it, but not at this slow speed that it just rolled down my driveway at. Okay, so now we need to know time to stop. So time to stop. This one is going to involve momentum. So we'll say part 5, time to stop. So we know the conservation of momentum and impulse and momentum equations. Now, momentum is not going to be conserved while the car is stopping because there's an external force applied, the friction force. So we will use impulse and momentum. So we remember our impulse and momentum formula is F delta T equals M delta V, which is M V final minus V initial, which in this case was the speed at 0.3, which was also the speed at 0.2. And the stopping speed, V final, is just 0. So in this here, we've got, we can rearrange and get that. Let's see, what are we trying to find? Oh, delta T. Okay. So the delta T, the stop time, is going to equal the M times the V2, so negative M V2 over the friction force, which was negative mu mg. So these negatives will cancel. And we'll just have that speed at 2, which is the 9.9, divided by the mu mg. And what do you get for time to stop? This gives us 1.44 seconds equals time to stop. Which, thinking about it, that is pretty reasonable. So like when I jumped in the car and slammed on the brakes, it did go like probably about another, it kept going a little bit while, and that was what, 7.4 meters, 2 seconds, or less than 2 seconds to stop, which makes sense. Okay. The 7.4 meters seems a little long, just like based on my memory. So maybe our coefficient of friction was estimate was slightly low. You know, maybe it was closer to 0.8. But overall, this makes a lot of sense. So looking at if we hit the mailbox, we would have a car and we have the mailbox. which that's a little bit big compared to the car, but oh well. And here we'll call this one state 3. And then this would be the new state 4. So at state 3, we have this car moving in here with speed of v3. Then the car hits the mailbox, and then they both, this is a plastic collision, so they both move now with speed at v4. So we need to determine now what is happening. What is the post-collision speed at 4? And this is assuming that no human jumped in the car and slammed on the brakes. The car was just left to roll on its own. So in a case like this, we would have conservation of momentum. So we're going to include just the linear momentum because angular and linear momentums cannot add together. So we just have to account for the linear momentum of the car, which really is more significant than the angular momentum because the wheels are so much smaller than the body of the car. And the wheels themselves also have linear momentum. So we will say that the mass of the car times speed of the car at 3 plus mass of the mailbox times the speed of the mailbox, which was 0, initially equals the combined masses. So that total mass plus mass of mailbox and speed at 4. So if there was a tiny mailbox and a big car, they're going to be going really fast. If it was a small car and a big mailbox, they would slow down. I mean, either way, they'll slow down, but how much do they slow down really is the thing. So here we can eliminate if the mailbox was not moving, it had no momentum at the beginning. Then the speed of the car at point 3 is the same as the speed it was at 2 because of energy being conserved and the drag force being insignificant. So we will say that mass, this should be total mass of the car times V3 over mass of the car plus mass of the mailbox equals V4. So we have the mass of the car, which is the 1,400 kilograms, times speed at 3, which is 9.9, over the total mass, which is the 1,400, from the car plus the mailbox, which we said was 15 kilograms. So 1,415. So if you plug this all into a calculator, then we get 9.8 meters per second equals speed at 4. Okay, so it slowed down 0.1 meters per second. So even if the car takes out the mailbox, it's probably going to keep going and hit something else. So much better that we stop the car.